Okay, in this short video, I just want to look at digital input, so pull up, pull down, resistor switch combinations, and then we'll just have a quick look at our LED and safety resistor. It sometimes causes a few problems in calculating the safety resistor value, so I thought I'd introduce it early. Okay, let's have a look at our pull up, pull down resistor combinations. Okay, so let's have a look at this first one here. So the resistor is at the bottom, down. So therefore, when the switch is in its open position, as it currently is at the moment, then the output voltage is being pulled down to this lower supply voltage here. So we switch open, output is 0 volts. As you press the switch, metal contacts across there to there, which means the output voltage then rises to 9 volts. So we get 9 volts when the switch is pressed and 0 volts when the switch is open. What does it avoid? It avoids floating voltages because we know that when the switch is in the open position, we know that we're going to get 0 volts here because of this resistor connected through to 0 volts. If we didn't have that, then this point here would float and there could be any voltage there. Right, so let's just make a note of that before we move on to the second circuit. Okay, so in the second circuit we've got the opposite. The resistor is up. So this is a pull up circuit. So in its current state, when the switch is open, the output voltage is being pulled up to the upper supply voltage. The output voltage is 9 volts. As soon as you press the switch, the output then drops to 0 volts because contact to contact, this connects that point there to 0 volts. Okay. So we just got a bit of design flexibility. So these two options avoid floating voltages. It's very good. It's good practice to put these resistors in now. And some microcontroller circuits, you don't have to do this, depending on the microcontroller circuit, but certainly it's very, very good practice to put these. Okay, let's move on to our LEDs. So there we have our LED, anode to cathode, means we need to have a greater voltage on our anode than we do to our cathode for it to illuminate. And you can think of these things as a diode here. We've got an arrow here, so we've got a current flowing. Current flows only in the one direction. Okay, and we've got a little bit of a ramp for the go up, so we need enough potential on this side to push the current up and over the ramp down the other side for it to illuminate. Okay, so our characteristic graph looks a little bit like this. So nothing happens in reverse bias. The LED doesn't illuminate because nothing happens. And then as soon as we get to this forward bias voltage, typically around about 2 volts for an LED, but it depends on the color of the LED, then we get a rapid increase in current there. So that rapid increase in current is why we have a safety resistor, because we want to limit the current flow, because our output sources do not have a limitless supply of current. Okay, so let's have a couple of examples of our safety resistors. Okay, so the first example here, quite a common one for a digital application. So that I've got 5 volts there, but that could be coming from any digital output process. So it could be coming from a microcontroller or some sort of logic gate or something like that. We're saying we've got a red LED that we're going to illuminate. It's got forward bias voltage of 2 volts and a 10 milliamp operating current. Okay, so we need to know what the value of R to have. So simple. Resistance equals voltage divided by current. Remembering voltage, it's the voltage across the component. Okay, that's what people always forget. So in this case, the voltage across R is going to be 3 volts, 5 minus the 2 volts, and 10 milliamps. So therefore, we get our 300 ohm resistor. Okay, quite simple, but quite a common type of question. So same type of question here. I've just switched it around, so we've got a LED this side of our safety resistor. Does it make any difference? No, because it's a series circuit, so we've got the same current flowing in both both components, so therefore the calculation is exactly the same. So remembering that we've got the 9 minus the 1.9 volts across our resistor here, the 15 milliamps running through, gives us an answer of 473 ohms. So one last thing, if 473 ohm resistor doesn't exist, but we could probably try and create one. So if we're going to choose one from the E24 series, then what do we choose? There's a 470 or there's a 510. Which one do we go for? Okay, we go for the next value up. Why? Because we want to limit the current. Otherwise, if we went for the 470, okay, a fraction of a difference, argue it wouldn't be made as 470, but we always go for the next value up because we want to limit the current value. Okay, right, so that's about wraps it up.